watch me code. It is about 11:02 a.m. and we're about to get started. So today, actually let's just recap where we're at so far because it's been about a week. So if I recall correctly, we got, what did we get? I don't know. Let me just go through and check. Let's see our notes. Twitch episode notes. Okay, so I think we were, I forget what we were doing. Let's just run it, see where we were at. Let's get this to be full screen. Let's go here, and let's do, okay, let's run it. I think we got the print network working, right? Hopefully. Let's run it. It's running. So if I recall correctly, we had a bunch of issues. We were trying to inject our network map into a bunch of different classes or structs or implementations or whatever to share it, but we ended up going and basically I think making a global network map somewhere. So network maybe got up here. Okay. Oh yeah. So we had the network map. We wanted to make it static, but we had some issues, so we had to use this lazy loading thing, right, to load it up. So on Reddit the other day, and actually, they added a feature to the language that I believe allows us to do this kind of natively. So let's go to GitHub and see if I start that project, and then we can go see about that. Where is it? Where's my stars? I don't know. Let's go here. Your stars. Ranger, no. Okay, so I might have started on a different account. Okay, let's see. Let's just go back then. So there's a few things I found. There's one, this feature to do this initialization logic, and then there's another one for an in-memory database I found that might be a good fit for the network data store versus using a raw map. So that's another option, and so that one is basically an in-memory, they call it an in-memory database that you can use, and it can take snapshots of that database. So I thought that would be a good idea for storing this information so that we can easily serialize it to a file and then reload it up as basically a backup. So we can have like a history of the network over time and not have to search up the network every time we start this server instance. But anyway, let's get back to, let's see, PN, print network, yep. And then what was it? Health check, and then remote address equals 127.0.0.1 and port equals what was it? What port are we on? 3001, right? Okay, so now we got that. We print network, and okay, that's where we're at. We got the ability to do a health check and add a remote server to the network, and then you can print it out with PN. Okay, so that's where we're at today. So the one thing we did was for downloading network maps from remote hosts. All right, let me just run this again. We made the where is it? Health check stack, network handlers, network broker. The health check stack. So we had, maybe it's network, network table APIs, right? Yeah, so this is our server, our HTTP server, and we're using this to serve down the network map from the current host, right? So if we go to the browser and we go to, let's go open up a new tab, we actually go to that endpoint 127.0.0.1 and then the port 3001, and then we get back right now an empty map. But if we then go and do health check, remote address equals 127.0.0.1, and then port equals 3001, do that, and then we go here, and then we can now download the map via HTTP to the browser, which is good, but today I wanted to basically replace this HTTP server with a custom UDP implementation, so that we can basically load this with UDP instead of HTTP. Yeah, it's a little overkill, so a lot of people would say, why are you doing this? This doesn't make any sense. And there's actually a Stack Overflow post that I'll just show you, but kind of motivated me to even want to do this. So adding what is it, reliability to UDP. Let's see if we can find it. What do you use when you need reliable UDP? What about SCTP? It has chunking capabilities. No, let's see. What do you use? Let's see. How do you make UDP more reliable? In a job, okay. UDP by itself isn't reliable. It's not reliable. Okay. Anyway, I'm probably not gonna find it, but I saw a post on like Stack Overflow or something like that, and somebody was using UDP, and they were asking how they can go about making it more reliable, right? And basically everybody was like, this is dumb, I don't know why you're trying to do that, just use TCP, or Google has their own implementation, just use that. Like, why would you ever go about making your own implementation? And so I didn't like that answer, especially on Stack Overflow, because somebody has to create these things. I mean, I guess not. You can just use whatever exists, but I'm not doing this because it makes any sense. I'm doing it because I want to see how I would do it and use it as a learning experience. So kind of saw that and was like, wow, these people are tearing him apart because he wants to do something different and redundant, I guess they would say, but anyway, whatever. So I'm gonna define this new protocol, and we're gonna use it hopefully if it works. So let me go back. Let me just another thing. I had a ton of ideas for where this project can go. So we'll do. Let me just put down the date, right, for 2024. List of ideas, right? So I took a bunch of notes on some ideas I had to give you an idea of where I'm hoping that this project can potentially go, and some of this stuff that I was thinking we could do. So This one, TCP replacement with custom reliable UDP protocol, right? So that's one. Well, this other one is unrelated. I thought it would be cool to run Express in the browser, like Node.js Express. And that's unrelated to what we're doing here, but it was an idea I had. I thought it'd be pretty cool. So latency map, in network map, and this would allow us to, do some, let me see. And then we could do some cool stuff with this, like best path. We could do application layer routing. And so what I mean by that is basically, like networks already do this, so like routers and switches and things like that on the IP level with the IP protocol will take your request and route it to other routers throughout the network to get it to its final destination. So the idea here would be to do that at the application layer. So instead of saying like I want this to go to IP address and port whatever on the network, I would say, all right, I want it to go to this IP import, then this IP import, and this IP import to send it to a specific path between the hosts on the network. And this like is more of just a way for me to experiment with the network because it's likely never going to be as optimized as what would happen by the routers on the network itself. Because it's going to have to do that routing anyway. So it's going to go through all those routers and it's going to try and find the best path. And we're going to be basically giving it multiple destinations. So it's going to, I don't know. It might be quicker, it might not. I doubt it's going to be quicker, but I thought it'd be cool. And there's some other ideas I had with that as well. Another one would be network discoverability and recovery. So the idea there is we're going to build off of our health check logic, and so we'll set up a schedule that these health checks will be made periodically to just check and see if the remote hosts are able to send back responses and prove that they're still online. And so that would be the recovery or checking the network health. Another thing we want to do is the network discoverability. So like kind of like what I was showing here. If I don't, where'd that go? Right. Like that. So that HTTP call we were making that returned the map, right? We're gonna basically have a way to call those APIs on our remote hosts, get their network map, and then any hosts within that network map that we don't have access to, or we haven't previously health checked and added to our network table, we'll basically, on a schedule, extend the network by making requests to those servers and learning more about them and adding them to our network if they're healthy. And then rinse and repeat that process. We ask those new hosts for their tables, and kind of from there we'll be expanding our context and knowledge of the network. And expanding our network table to include more remote devices. The recovery aspect of that is, like I mentioned, we'll do health checks on a regular basis, and so after X amount of failed health checks, depending on how many lives a host has, once those reach 0, they'll be pruned from the network, and we'll remove them from our network table. And then basically it'll be gone until, say, it joins the network back and we reconnect with it. So that's how that'll work. And another one, I bought wanna learn to code.com. So I part of the reason I'm like doing all of this is to show people like what it's like to code, and hopefully teach them some things about coding that they can then take I don't know if anyone's watching, but basically get people interested in coding and showing like what you can kind of do with it, because it's something I'm really passionate about and really enjoy doing, and I made a career out of it, and so I want other people to kind of, if they want, or have motivation to pick this up and make a career out of it, or learn it just in your free time, expand your knowledge of it. So I wanted to take Want to Watch Me Code, and take it a step further, and at some point teach courses on this, like give pick a language and start with the basics, and then kind of go through that language and show you all of the details about it, so that you can ultimately, by the end of the class, hopefully write your own programs and use it as a starting point for expanding your knowledge of programming, and see if you can kind of get into it and eventually create your own applications. So with that, not going to do that for a bit, but on Want to Watch Me Code, this channel, I'll probably do a series where I'll actually create the class structure and come up with material for the class, so that I can kind of document how you can go about teaching and creating a teaching plan, and then I'll execute it, and I'll film it live, and then I'll create the website and post all this stuff to it. And along with that, I was thinking doing something like Code Academy, so like a code editor in the browser, so kind of like what's it called, Code Academy, I don't know how you spell it, Code Academy experience, so that you can actually I want to give sample test problems and make it possible for anybody to go into the website and kind of write code and test it out and follow an example problem, and maybe give hints and stuff and examples, so that you can kind of learn on your own without having to download your own IDE and editor and all the languages and stuff, just kind of being able to do it in the browser. So that's that. We had the best path calculation, so I don't need to add that again, and just come on. Okay. Okay. Another one. Whoops. Let's close that. So another one, end-to-end encryption on network, right? So the idea here is, since everything is so decentralized, I want to come up with a strategy for keeping the network secure, and ensuring any data going across it is secure in a new way, aside from SSL certs and things like that. So the idea here is everybody would have their own keys, and those would be used to encrypt the data from client to server and back. So, but the idea here is that the keys would be owned on each device, right? So, when you're a client of the network, you want to send data securely. You would generate your own public-private key pair, set up a connection with the remote host you're trying to transfer that data to, give them the public key. They would give you their public key, and then you could perform encryption on either end, such that only the destination host would have the ability to access that data. Another benefit of that is I'm thinking we'll generate unique key value private public key pairs per remote host, right? So basically we're going to try and guarantee that only one host has access to these encryption keys, so that we can use that to determine the source of the information coming in. So right, so like if only one server has the public key to encrypt data that they're sending to you, basically if it's encrypted and you're able to decrypt it, you have some ability or some certainty that that data is coming from where you expect it to be coming from. Now that's not 100% true. If that key does get hijacked, then there's potential that you could be getting requests properly encrypted from a bad actor, right? That could be trying to imitate the source of that message. Now, in that case, it shouldn't be that big of a deal because although they can encrypt it and send it to you as if they were the person you expect to receive the message from, if you send a response back to them with their encryption key, their public encrypted data, the bad actor would get encrypted data that they would be unable to encrypt unless that private key is exposed, which shouldn't happen because that key should never leave the host that owns it. Now, like that's anything can happen really. Like that key could get stolen, or somebody could accidentally transmit it or expose it. So there's potential, no matter what, for this data to be exposed if we don't have the proper layer of protection for the storage of those encryption keys. Anyway, got that, and then the other thing is skip DB, right? So this is that in-memory database with snapshotting, and so this is a new library I found last week when just browsing Reddit. So it might be something that we want to incorporate for our network map, basically. Okay, so these are some ideas, and we'll just start with the TCP replacement with customer reliable UDP protocol. So now I'm gonna start a new project for this to keep it kind of decoupled because this one's getting a little big and I didn't do too good of a job organizing it. So I'll just and these can kind of be decoupled. So the UDP protocol I'm going to create can be a separate package, and when we want to use it, we'll just import it into this package as a dependency. So let's go ahead. We'll create a new project. Right, REST server projects. I don't know why I put it there. Let's go here. Let's go in here. Bring this over here so you can see it. REST server projects. Users, REST UDP, wash code, source, SWDs, repos. Can I create? New directory. We'll do decent, right? Let's just do decent workspace. Okay, and then we'll do go here, and then we'll do decent. I'm gonna drop the SWDI prefix. Decent UDP. Okay, create that. Okay, let's go. No. Okay. Why? A specified path cannot be found. I'm so confused. So if I do this, okay. Decent UDP. Okay, does that work? Let's try, let's do library here. Create new window. Now let's just stop this from running just in case. And yeah, so also one other thing. Let me see. Let me just check something. Let me go here. Let's go to Twitch on my phone. Let's go here, live, I'm live. Let's go, turn this down. Test. Okay, there's sound. Cool. Alright, sorry guys, I'm just checking some things. Go to Stream Manager. Okay. Yeah, cool. So let's go there. We created our new project here. Well, okay, let's, I don't know why it does this all the time. Like, can I, okay. Oh my gosh. Okay. Let's go here. No, what is this? It works. Source. Okay, cool. Project not associated with cargo.toml. But cargo.toml's there, right? Attached cargo.toml. Okay, I don't know. I don't get it, dude. What the hell? Cargo.toml. Okay. Oh, am I not supposed to have a cargo.toml? Is it supposed to have cargo lock? Okay, I don't know. I don't know why I did that. I don't know if it's supposed to do that, but why? What the hell? Don't like attach cargo.toml. What? I don't get it. It's there though. It is though. It's like right there. Why is it complaining about this? I'm gonna close it, dude. This is stupid. Let's do open. Decent UDP. New window. Okay, is it attached? What do you mean it's not associated, dude? Okay, is it good now? Okay, jeez. Alright, we good? Or no, probably not. It's probably not gonna... Okay, looks like we're good. Why did it do that? That's weird. Okay. Alright, so what are we doing? Let's do readme. Get the readme. Readme.md. Go, cancel decent UDP. Let's go decent UDP. Okay. Let's commit this. Okay. So, new folder. See source, repos, decent UDP, get status, get and get ignore, idea, cargo lock, readme source, get status. Let me just check something. I remember you're not supposed to have cargo.toml. Okay, let's go in here. Let's go. Cargo.toml versus cargo lock. Cargo.toml and locks are two different yeah. Describe dependencies. When in doubt, check cargo lock and diversion system for a better understanding of why. Okay. Is it manifest? Okay, I guess, yeah, it says when in doubt, commit it, so do that. Get status, actually should I get Actually, let's create our repo. Let's go one watchman code, repositories. Okay. Just am I logged in? Like a new. Let's do decent UDP. Let's do public. Let's do a get ignore of Rust. Let's just add a README. Let's do license MIT. Actually, let's not add a README. Actually, yeah, let's do that. Screw it. Okay, Rust, MIT license, add README, create repository. Okay, got that. Let's clone it, or let's, how do I don't want to clone it. How do I add a remote? Get add remote. Get remote. Okay. Below is used to add remote. Okay. Add origin. Get remote. Add origin. Okay. Go here. Get add remote. Origin. And then we'll go like this. Okay. Get remote. Add origin. Paste. Get status. Is it main? Okay. Get stash, get checkout main. Alright, whatever. Let's just do get checkout origin main, and then we'll do, what do we got? License. Oh man. Alright, now we're just gonna license README. What's the README at? Okay, so it's just the same. Let's just do this. Oops. Oh my gosh, dude. These shortcuts are killing me. Main. What? Okay, get status. Yeah, this is ridiculous. Let's get a license. Okay. New file license. Okay, MIT license. Add. Get status. Get add on idea. Get Okay, git commit. Initial commit. Okay. Alright, whatever. We just did all this for seemingly no reason, but whatever. Okay. Okay. Alright. Got our initial commit. Okay. And then we'll go to readme, and then we'll do decent UDP is a reliable UDP protocol. Okay, and then we'll do protocol. Okay. Okay, so what are we doing? Okay. What are we doing? Let's see. Okay, I know. Okay, I got it. Okay, so how are we gonna do this, right? Let's just go over some background, right? So, let's go back to our previous project where we have some notes on this. So, where is it? It's not on here. It's probably in the README, right? Hopefully, let's go look for 508. Yes, here we go. Okay, so 508 bytes max. Let's just copy that over. Okay. Pepper. Okay. So this is our so restriction on guaranteed single packet min size, right? So it's 508 bytes. We're guaranteed to not have our UDP packet data broken out. It'll all be in a single packet. Anything beyond that, to a certain extent, might not be split, but it depends on basically the devices on the network that we don't have control over, but minimum 508 bytes are guaranteed to get there. I mean, hopefully, I that's what this post said. 508 bytes will basically hopefully get there in good state. Pepper! Sorry, cat's going nuts. Just eating air. Okay, so we got that, but that might not even really matter. So, one thing is so some concerns we have are a single packet may come, or a single packets over 508 bytes can be split up and received out of order, right? So that's one. So we have that. Sorry. And then another concern we have is that packets can be received in corrupt state, right? So I don't know if a single packet would come in corrupt state, but what I read is that there's a checksum on the IP packet that is intended to guarantee some sort of basically it's supposed to detect some corruption, but the problem is that apparently the checksum they use can have collisions. Pepper. Yeah. So hold on. Sorry about that. Okay, so yeah, so they can come out of order and they could be corrupt. So how are we gonna mitigate that, right? So one, for the out of order, we'll have a sequence number in the header, right? And so each packet we receive will have this sequence number, and it'll allow us to detect if any packets are coming out of order, right? So say we have 100 packets and they're labeled, say, 0 through 99 by index, or maybe it should be starting 1, I forget. But anyway, when we receive, say we receive packet 1, 2, 3, and then we receive packet 5, and then we receive packet 4. This sequence number will basically allow us to detect that. Another thing for corrupt state, or data, I guess, is we'll have a checksum, right? Basically, what a checksum is it's a value that is generated from hashing data, and it gives you a specific number every time you give it the same data. And so you'll take the raw data like binary, you'll pass it into this hashing function. This hashing function will generate a bunch of random data that comes up. Well, it'll generate a bunch of seemingly random, characters like A, 1, 9, like whatever random characters. And so when you pass that data in, it'll generate that. And then when you pass that data in again, it'll generate the same output data. So the idea is that before we send the data and transmit it from the sending host or sender, we will hash the data we're sending, and then we'll provide that key in the header of the packet such that when it gets to the other end, they can take the payload data, hash it with that same hash function, and then compare it against the checksum in the header. If it matches, then we can, with reasonable confidence, say that the data was uncorrupted. If it mismatches, then we'll have to do redriving. Why is this that's weird. Okay. I don't know. Okay. I don't know. Okay, so checksum for that. That, and then let's go. Okay, got that, and then what are we doing now? So we're doing out of order. Okay, we already have out of order. And then we also have to worry about lost packets, right? Because the packets aren't guaranteed to be received on the other end because we don't have a connection and we're not getting back acknowledgements by default. So by default, we're not getting back acknowledgements. And so we have to have a way of getting those lost packets back. So we're going to do this by redriving missing packets after X amount of time, right? So we will basically collect this data in a buffer. If a packet's missing, then we will request from the remote server to the sending server to resend that missing packet, right? And then hopefully we can mitigate that. Another thing we have to worry about is this is more longer, but network congestion is another thing. So, for example, we're going to be transmitting this data, and there could be various different loads going on. So, they could be transmitting this data to me, but somebody could also be transmitting data to them. And so, say there's just too much data being sent back and forth from different hosts to different hosts, and so it could potentially overload any one of the servers on the network. So, what this means is we have to have a way of slowing down the amount of requests going around the network. So for this, I haven't quite determined exactly how we're going to be doing this, but basically we have to have some sort of back off logic. So what this means is we have to have some way of saying to whoever is flooding you with data, hey, wait X amount of time and try again because you're sending way too much. I can't handle all of it. And so another thing would be like throttling, right? Throttling or load shedding. So these kind of go hand in hand, right? So, and in fact, I think throttling and load shedding would go before back off, right? So, the throttling would be like, all right, so like I'm getting bombarded by, say, my one friend and my other friend trying to talk to me. So what we're gonna do with throttling is be like, oh, you're sending too much stuff. We're gonna say, just ignore like X amount of these packets coming through and worry about your other chat with your other friend or your other server. So we'll basically just like not allow too much to come in from a certain source if they're overloading us. So we'll shed that, but we also need to recover that data that we're basically ignoring, and so we do that by giving some sort of indicator to the very greedy server sending a lot of stuff to basically slow down. So it's that. What else? Okay. Yeah. So I said that we wouldn't be having acknowledgements, right? But we might have acknowledgements. Yeah. The one thing to worry about is like too much back and forth. So like, if I don't know, we don't want to get caught in a situation where we're like causing even more, like basically causing even more requests to go through. So, which we do. I don't know, but anyway, we haven't written any code yet, so like let's get to it. Let's just go off of like I'll go through these in order. So, okay, protocol. Considerations. Okay, let's just do that. Okay, I'll do protocol. Okay, protocol, and then we'll do. Okay, what are we gonna do? So each protocol will have a header. Right, and then we'll have a payload. Okay, so go like that, and then the header will contain, let's say, opcode, similar to our other protocol. Just go like this, opcode. Sequence number, or let's just do sequence. And then we'll do, what is it? Sequence, opcode, and checksum, and then payload. Okay. And so one thing I'm actually thinking is like making this like more configurable, if that makes sense. So one thing I kind of want to do with this is make it so that I can optimize for different things and configure this in a way that's like kind of dynamic. So one open question is, do we really want to limit the packet size to 508 bytes, or do we want to just do extra checks on validation on larger payloads, and just validate that if a UDP packet is very large, that we actually get all of it in order and it's not corrupt. So part of that is like I want to experiment with that, right? So I'd like to try with the 508 bytes max, but I'd also like to be able to try with larger payloads, and compare some of the characteristics of them. So like with the 508, I want to see that we have less issues with corrupt data. See what the rate of corrupt data is as we extend the size of the packet. So like say we do 1024 bytes, we have no issues. We go to 2048 bytes, and then we start seeing like say 1% degradation of invalid packets, and then like go from there, maybe raise it lower and figure out the ideal state, and then and then that'll get us into a redriving of the packets in that case, and then kind of seeing is it worth doing larger packet sizes and having a higher error rate and redriving those and retrying, or is it better to have smaller packet sizes and having less corrupt data and the first time we receive it is correct, I guess. So is there some considerations? Yeah, so it's that. Now, what are these sizes going to be, right? Okay. So yeah, what are the sizes going to be? So, so it depends on the max amount of data we want to send, right? So, yeah. So I kind of want this to be optimized for small data. Or let's do some math. What are we trying to do even, right? Like so we want to send the data, we want to send the network map. What are we trying to do? Okay, let's get into some of the, like, what we're actually trying to do. So we want to start a file transfer. We want to send data, and then we want to confirm data received. We want to redrive failed or missing packets. We want to have back off logic, back off request, back off request. Okay. So start file transfer, and we'll just have no op. It'll just be 0 at 0. Okay. So how many instructions do we need? 1, 2, 3, 4, 5. Okay. Okay, so let's just do these in order. 0 at 0, 0 at 0, 3, 0x 0, 4, 0x 0, 5. Okay, so got that. Opcode. Okay, just copy that. Got these. Alright, got that. Let's do, so opcode will be, let's just actually do this inline, so, so this will be 0, this will be, let's see, I just wonder if I should make this forward compatible for new opcodes and make it bigger, or make it minimalist and small. Okay. I could also have an extension bit, right? Like if this is, so this is F, then we could make this bigger, I guess. But okay. So right now, what is this? Okay. 2 bytes? Hold on. My binary math is so off. Let's do hex. Hex size. Hex font size is 1 byte per thing, right? Hex format. Base 16, right? It's base 16 hexadecimal. We're using a radix of 16 for base 6. Pepper! Alright, okay, so base 16, we just do FF2 bytes to binary. Let's see what it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, so it's 1 byte. So two things are 1 byte. Okay. Okay. Wait. FF answer convert hexadecimal. Okay. Yeah. So it's 1 byte. 1 byte. Okay. Sequence number. Right. So let's see. How much data we need? Sequence number. How much data do we want to send, right? So it depends, right? How big is the packet? How big is the payload? What is the largest amount of data we want to send? Actually, let's see. 64-bit addressing. 64-bit memory addresses can directly access to the 64 bytes, 16 exbit bytes, or EIB, of byte addressable memory. Okay, so that's a lot. With no further qualification, a 64-bit computer architecture generally has integer addressing registers that are 64 bits wide. Let's see. How big can a sequence number be? TCP. 32-bit. Okay. So that would be 2 to the 32nd minus 1. 4 giga sequence numbers. Okay, so be able to send only 4 gigs of data with unique sequence number, not more than that. Okay, so there's wraparound though, right? So four giga sequence numbers. So we can get 4 gig sequence numbers, which is what, like 2 to the 4 times 2 to the 9th, right? Is that, what is a gigabyte? So let's see, a megabyte or a kilobyte is 1,000, so 2 to the, or 1024 divided by, or what is 1024 divided by, or 1024 to the okay, so 8 to the 3rd, right? 8 to the, 8 to the 4th, 8 to the 3rd, 512, bytes in KB. 1 KB, 1000 bytes. Oh my god. That's 10 to the third, right? 10 times 10. I hate that, like, it's not, like, gigabit. What? This makes no freaking sense. Nibble, like, why do they gotta change these things? It used to be base 2. Okay, alright, what are we doing? What are we doing? Let's go here. So sequence number, let's just make it 8, 16, 4 bytes. Okay, and then checksum will be checksum. Parity byte or parity word sum complement positive dependent fuzzy check. 120-bit MD5 hashes. So like the smaller our packet size is, the least precise or the less precise the hash has to be. So MD5 we probably don't need that. There's theoretically an unlimited number of files that will have any given MD5 hash. However, it is very unlikely that any two non-identical files in the real world will have the same MD5 hash, unless they have been specifically created to do so. The underlying MD5 is no longer deemed secure, thus, while MD5 sum is well suited for identifying known files in situations that are not security related, it should be not be relied on if there is a chance that files have been purposely and maliciously tampered. Okay. IP checksum. I just 8-bit checksum. Writing 8-bit checksum in C. Okay. Not secure. Okay, the 8-bit checksum calculator can be used to calculate 8-bit checksum of a sequence of hexadecimal values or bytes. Bytes can be to do 8-bit modular. Max safe checksum. Minimum checksum by data size. No minimum required length. There's no minimum required length for a checksum. You can checksum things of any size. Ethernet frames are typically 1500 bytes and only use 4 bytes for checksums. If you want to be on the safe side, use SHA-1, but it takes up 20 bytes and can be slow to calculate. To put the result of CRC into the array, you need 4 bytes, 32 bits, 8 bits per byte. you're asking how big it should be to detect corruption, that is a really hard question. Firstly, no matter how large your checksum, no matter how it is calculated, you can never completely eliminate the possibility of an undetectable corruption. Even if there's many checksum values as message values, you can you could use any checksum algorithm you wanted, even a 1-bit checksum, parity bit, or even 0 bits. A 100% reliable network doesn't need checksums. Your code as written uses CRC32, it is 32-bit or 4-byte checksum. Irrespective of the number of bytes of data being checksummed, however, it appears to only be passing the least significant byte of the CRC32 in the data out message. Unless the receiver is doing the same thing using only the low byte, the checksums won't match. Okay, let's see, CRC32. Okay. Data integrity, okay. So let's just do, let's do 4 bytes. CRC, and then this would be so this will be 4 bytes, 1 byte. What would 2 bytes be? 32. 2 bytes max values. Okay, so 2 to the 16th. It's 255, right? What? Really? Is that right? Oops. 2 to the 8th, right, is 256. Okay, 2 to the 8th can have 256 values. Yeah, okay. Yeah, it should be enough. Wait, 2 to the 8th. 256. Okay, that should be fine then. So 9 bytes. So then we can have 499, right? Bytes. Okay. That's a little weird though. Do we really want 499? Okay, yeah, let's just do that. Okay. Cool, so we got our protocol. Okay. Alright. Should we start writing code actually? Should we do that? Okay. Do Rust protocol. So this will be, let's make these our like constants, right? So let's do let's go, no, let's do opcodes, right? Okay, add, do that, we'll do, whoops, okay, we'll do const no op equals 0, 0, 0, does that work? And this will be a U8, right? And then const, kind of want to make these silly names. Let's go initiate transfer equals 0, 0, 1. Let's go U8 const send data U8 equals 0, 0, 2. Okay, const data act U8 equals 0x 0, 1. Oh, it's not 1. Actually, let's do receive act. Receive act. Const redrive U8 equals 0, 0, 4, 3, const redrive, and then back off U8 equals 0, 0, 5. Okay, it's opcodes, right? Got that. Protocol, we'll do as protocol, copy these to opcodes. Okay, got that. 1 second, be right back. Alright, back. Let's go. Let's see. Okay. Okay. And then let's take a look at our old code because we did something very similar to this, right? So we got health check, we got the op code. Okay. Okay. Let's do struct decent packet, right? And then this will contain our protocol, so it'll get the header decent packet header, go like that. We got, and then payload decent packet payload, right? And then we'll just get these destruct decent packet header, right? And then struct decent packet payload, right? So got those. The decent packet header is going to contain the opcode, and then this will be U8. Got and I don't know if this will be U8 or if I want to make an enum, and then we'll do sequence what was this, U32, right? And then we got checksum. Okay, so you should be lowercase. Opcode checksum will be U32, right? Or is it 4 bytes? Yeah. And then payload. No, not payload. This is just the header. And then payload. Yep. Decent payload, and it'll be okay. 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 Should we just make payload? And then this will be data will be U8 back 8, right? And then because I kind of want to make this variable. Okay, got that. Let's see. Did I make this a constant size? No, let's not make it a constant size. It can be variable. Okay. Okay, that's the protocol. Let's do serialization. Serialization, right? And so we're gonna go a different route than the last time. We're gonna make this more functional. So we'll do fun, pub fun, serialize. Actually, hold on. I kind of want to use surd, and maybe then I can just make it more generic, right? Let's see. Let me go to surd documentation because I don't really know how it works. Rust surd. Surd Rust doc. Okay. Data format JSON, YAML, BSON, Evero, URL, dbus, token streams, Dynamo, DB items. Really? Wow. So they're just binary. MV store, dbus, binary wire format, CSV, D. Generic data structure serialization framework. Surd generic data structure serialization framework. Okay. Deserialize, derive. Traits, derives, macros. Modules. D. Primitive types, compound types. custom CERD serializer. Okay, CERD default. How does CERD work? Custom serialization CERD. Okay, let's just try this. Let's go here. Okay, not that. Let's go here. Just go like that. Serializer, we gotta select expanded macro. Okay, how do I search derived macro through serialize, deserialize, revise using the default serialization for structs and enums, and it can be customized to some extent using attributes. For unusual needs, CERD allows full customization and serialization behavior by manually implementing serialized and deserialized traits. Okay. So let's do, how do I get CERD? Implementing serialize and implementing deserialize. The serialized trace looks like serializing a primitive. Back here, using derive, add CERD. Let's go here, cargo toml, go here, go like this, go like that, go like that, go like that, go like that. Okay, got that for proto. Go to protocol, pub, and pub. Right, so we got that. Decent packet. Okay, let's go. Deserialize. I gotta do import. Okay, let me just. Okay, let's go. I-32 visitor. Import DE from visitor. The visitor trait. No, this looks like what it's supposed to be. It's taking forever, dude. decent packet. Okay, deserialize. Okay, finally it finished. Maybe, no it didn't. Oh man. Alright, let's go. Okay, cool. For decent packet, deserializer D error. Enum field. Okay, let's look at the example. Sex nanos. Nope. We want. That's interesting. Dude, actually, let's go back here. Opcodes. Let's make these enums. Pub enum. Decent protocol opcode. And go like this, like that, like that. Let's go to Rust enum. Rust enum, geeks for geeks. Can we give them values? Froze. It's frozen. Okay. Output January. This is so slow. Oh my gosh. You're so slow, AI. While struck feed. I'm confused by this, right? People field declaration. Does that work? No. Yeah, screw it. We're not doing this. I don't think oh no. There we go. Alright, we're not doing that. Pub. Do we want this? Okay, whatever. Let's just go here. Field. Let's do. Field would be opcode. Sequence. No. It'll be header payload. Okay, maybe. Where field visitors, visitor value equals field expecting formatter. Wait, I don't know, man. Sex. This isn't what we want though, right? Deserialized field visitor. Where's field visitor? Duration visitor. Visit map. Damn, dude, I don't know what this is. Insert custom binary protocol. Insert binary. Ooh, maybe this is what we need. Serialize and deserializer for binary data sequence and maps that encode a length prefix of U32 for portability across platforms, which limits the number of items in sequence and maps to 2 to the 32nd. Type definitions, encode, functions, decode. Okay, this might be exactly what we need. Insert binary decode. Okay, it's not clear exactly. This isn't my first answer like this, but smuggling data into a deserializer always ends up extremely verbose for me. You need a deserializer per data type, JSON value of decided shape, and level inside of your data. In your case, there's 3 error results. 2 deserializers need to be written by hand for the top level deserializer. Our goal is to recognize whether we have error results. Okay, let's do custom insert binary deserializer. And let's ask AI if it knows how to do this. Copilot. Custom serialization, okay. Okay. Just copy this. Okay, go here. Just do that. Go here, go like that, go like that, go like. Can I do back U8? Custom deserial. Okay, so maybe this is all I need. Now I guess I got. What do I got? Okay, let's just let's go here, do that, go like that, go like this, U8, vec, U8, right, that, got that, and then, okay, cool, let's go, raw data, and then we'll go like this, we'll do raw data for now.